Thanks everybody for taking a bit of your lunch break. It was your lunch break to do this first lecture series as part of Gobble and Cost Action. Today I want to talk to you about taste, right? And how we have taste in our choices in knowledge graph construction. And what I want to particularly call out is how uh, AI systems have made these sorts of choices more important or maybe more as a source of value in the construction of databases or knowledge graphs. Before I start, I just want to give a little bit of a background about what we do at INDElab in particular. Uh, we're kind of broad goal is interested in AI systems fundamentally that support people in their work with data and information, in particular from multiple sources. And I'm always interested in empirical insights. So, what do actually people do, and how can that drive our research? So the group is this. We have about almost 30 people working on this subject. A nice thing I'll point about is that there's quite a few team members who are involved in Goblin. So Lisa here and Jan Christoph, and I think Hazar is doing a little bit of work in the Goblin cost action. So this is a team, and we kind of work on a lot of different stuff, but in this kind of general theme. Um, but in particular, we work on kind of three big research topics. One is automated knowledge graph construction. So how do we build knowledge graphs from these multiple sources? How do we do that with multiple modalities? How do we use LLMs to do that? We are also looking at context-aware data systems. So you can think of uh, data systems that know about the context they're in, whether that's the human societal context they're interacting with people, or more digital twins areas. So that's context-aware data systems. And the last kind of major theme is what we call data management for machine learning. So this is how do we support AI systems or machine learning through data management techniques. So you can think of this as things like data quality assessment, how does data handling actually impact ML models, and things like how do I find the data I need to build a machine learning system. So that's what we do. If you're interested in those topics, check out our site. If you're in Amsterdam, come say hi. We're always happy to have visitors. Um, as part of the lab, one of the things we like to do is actually build knowledge graphs, because I think, again, this comes back to this idea of looking at empirical practice. And so today I'll be talking about some of the how we have looked about out at these knowledge graph construction processes and how that has influenced this thinking on data taste. So these are some examples of knowledge graphs and data sets we've built. BasilDB, which is about a knowledge graph around biosemantic or around bioactives from the medical literature. We have FashionDB. This is a knowledge graph about fashion information. And then we have a database called Git Tables, which is a corpus of relational tables mined from GitHub. So in these processes, we think it's important to build these sorts of resources. They also influence our thinking on knowledge graph construction processes. So that gives you a little bit of context about who we are. Now let's talk about knowledge graph construction, in particular knowledge engineering, so the kind of wider view of knowledge graph construction. So this is a graphic that I'm quite enamored with. I like to show it a lot. It's from one of our team members, Bradley Allen, and it looks at knowledge engineering requirements over time. And the interesting thing is that over time, we've thought about when we build these knowledge-based systems or knowledge graph-driven systems, we've built up requirements over time of what those should be. So, for example, we learned through the first part of um, the semantic web is that we should be scalable and that we need to be globally distributed and we need this idea of interoperability. And the way to accomplish that is through kind of open and web-based standards. We learned in the semantic web era and a little bit after that, that we need to make developer-friendly systems that are kind of robust or integrated with software engineering norms. Um, we've seen that we have to have heterogeneous query methods that are robust to incompleteness. We've learned that we need to develop systems that are federated, right? And also that they should be open source. And through this era of the language model era, we've learned that we need data that is systems that are editable and that are accessible and that are explainable. And so all these requirements we have for producing knowledge engineering systems, we need to meet somehow. We need to build systems that are able to meet these various requirements. And so I think a fairly easy thing to say is that AI is making this easier, and in particular, large language models, right? So I think we've had a kind of starting back a couple of years now, this idea that knowledge engineering, uh, that LLMs can help us with these knowledge engineering tasks across a wide range of areas. And in particular, I think a lot of people on this talk have been thinking about how we do this, right? So I've been very happy to be in the Goblin community, in the broader community, thinking about these topics, right? So back in 2022, we had a Dagstool report that highlights the importance. So this was just right before ChatGPT about how knowledge engineering can use LLMs. We had knowledge prompting hackathons. We've had special sessions at both ESWC and ISWC. So we've had special issues. So there's been a lot of work going on by all of you about how can use AI systems to address those knowledge or AI tools, in particular LLMs, to address those requirements that I was talking about before. And uh, this is a great example of exactly this. This is a recent paper. I think the official version just came out this year from Elena Simperl's group at KCL, talking about, the how large language models can help us produce this. And we were happy to be part of this hackathon. I think Fina's on the call, and she was at the hackathon, and maybe some of you all were there as well. Again, learning about where we can insert large language models in this knowledge engineering process. And to do that, there's lots of, as I showed you, a lot of literature out there. This is a nice paper I really like by Daniel Garijo, kind of looking at the various parts of the knowledge engineering process and where, in fact, you can apply LLMs. And I think we can all know that building knowledge graphs and doing knowledge engineering is significantly changed and I think made easier by these LLM tools. So that's kind of the context. And now I want to talk a little bit about like an actual application and then kind of help you motivate where I think this choice that I was mentioning kind of comes into play, this idea of having taste. And I'm going to give you two examples, but let's start off with one. This is about knowledge engineering in practice, so building a knowledge graph-based system, right? And this comes from a startup I co-founded a couple years ago called longform.ai. And so longform.ai, what we do is we listen to um, 100 thousands of podcasts or a couple, well, 800 podcasts, even more in some cases, hundreds of thousands of episodes, many millions of minutes of audio data. And from that audio data, what we do is we extract and build a knowledge graph. And from that knowledge graph, we produce views or data sets. You can kind of see them over here, right? So advisors and challenges and those kinds of things. So we produce a knowledge graph and we kind of build data sets on top of that. And that's what we make available to folks, right? So this is longform.ai, and has a workflow that's very LLM based and very, like for you guys on the call, probably stuff that's kind of very bog standard. So this is not like a super research project. This is really just taking technologies we know about, taking LLM technologies and putting together to build this system that takes and builds a knowledge graph and data sets from podcasts. So we have an audio registry. We transcribed all that audio. Uh, we use LLMs to do extraction at scale. And then we have a validation technique. So every time we're extracting information, we actually run it through another LLM validation step that makes sure that the extractions are of high quality. That's produced into a knowledge graph. We also produce embeddings over that knowledge graph to help us resolve entities. So just classic things we do all the time in this community. And then we push that back into a knowledge graph. And now we expose the knowledge graph in a couple different ways. One is we produce these data sets out of that. And then we also provide those data sets through an API that you can access by like a REST API or a model context protocol interaction, right? And we also have a separate LLM agent that's going through constantly and kind of curating the knowledge graph to make sure that it's always high quality. So that's the workflow. This is not the, this is kind of taking things out of the box, doing things that we know how to do. But what's the value, right? So what are we doing that makes this interesting for people to use this knowledge graph? Well, there's a couple things, and this is where I think having built this, where this idea of taste and choice come into play. And so let me talk you through those ideas. So this is the idea of data taste. So we as knowledge engineers, and I think we've I think we always know that there's this idea that the knowledge engineer or is working with the subject matter expert to kind of figure out what's important in the domain. So there's always this underlying theme of what's important and having kind of taste in our research. But I think we've spent a lot of time on technologies or fundamental technologies just to do that information extraction, just to do the entity resolution, just to help us build large-scale ontologies. So that this idea of those kinds of choices has really not been at the forefront of our minds. And I think given that it's become so much easier, that these sorts of choices now are much more important to think about. All right. So some ideas of data taste. So I have a couple here. So one is source selection, where we focus when we do extraction, how we design our schema as taste, where and how we do our interlinking, and obviously telling people about where things are coming from. So I'll just walk you through these examples from this longform.ai system. So first, source selection, right? So when we actually build our knowledge graphs, we're building it on top of sets of podcasts. So my co-founder and I, we actually make a source selection. We say these are the set of podcasts that we think have quality underlying data, right? So we've already made a choice there, and we do that based on um, our own ideas about what is quality, right? And now an interesting question we have, and it's an interesting research topic. So can we take our notions of quality and actually build those into an AI system that can do that choosing based on our ideas of what's important? So source selection, already a form of choice, already form of taste. Extraction. So we choose what types, classes, relations that we extract, right? And so this is an example of our pydantic definition of what a founder is, that we're going to extract an organization, and that we're interested in dates, right? So when a founder was associated with a particular organization. So this definition of a type is exactly the definition of what we focus on when we take things out of underlying data sets is another form of deciding, right? Deciding and choosing what we convey in our knowledge graph. We build a knowledge graph. In the case of a long form, we actually just put our knowledge graph in SQL and we adopt a schema that looks a lot like Wikidata. And there's a choice in that, right? Into this idea of flexibility and the idea that we want references or pointers to all the underlying data sets. Now, when we have this knowledge graph, one of the things we do is we expose, I showed you these data sets over here. We expose these data sets for folks, for users, based on writing essentially views, right? So you can think of this like a Sparkle construct query or whatever, a view over our knowledge graph. So again, we're deciding which of these, what sets of relations and types we want to bundle together and make available to the users over an API or even AI systems. So again, we're making a choice. All right? Lastly, we decide what we link to, right? We're a lot of folks here are in the semantic web community, right? We're interested in identifiers, right? And those links that we create. So where are we linking out to, whether it's Wikipedia or Crunchbase or other standard things, and that ability to connect across different entities. And again, this is our decision, right? These relations that we have is our decision. The schema that we design is our decision. Those are important, right? And now it's pretty easy to develop these systems, but we have to think hard about what that means, right? And lastly, that fact that we have provenance throughout the system, that we are making the choice to make sure that we can tell you for every fact that we have in the system, which podcast that we got it from and actually where in the podcast it comes from. So we made the choice that we're going to have that attribution and that transparency, right? And so all of those are choices, all of those are my taste, right? And my co-founder's taste, right? And this has impact because even if you plug this into an AI system, so we have I said a MCP protocol access, you can wire this up and we do this into things like Claude, right? Or Mistral, you name it. And what happens is, you can ask it to produce a report based on this underlying tool, based on this knowledge graph. And the whole range of choices that we made in building the long form knowledge graph gets exposed to this LLM. So we've shaped what the AI system will respond by all of those choices, right? How the AI system will build this report is shaped by the data that we make available, the schema that we make available, what it can query, what it cannot query, that we have this provenance, makes the reporting that comes out, right? So it's not just the entire web, right? If you do like a normal deep research query, it's what we've shaped by building this knowledge graph. And so my claim here is that what's interesting is all of those choices. And can we make it easier, or can we think about how to elicit those choices, how to document those choices, and how to integrate those choices into our knowledge graph construction and our knowledge engineering process? All right, so that was one example. I hope you get the kind of gist of where I'm going, what I think is interesting, and where you might see different research opportunities there. So I'm going to give you another example. So this is work we presented just at the latest KCAP conference in Ohio on uh, embeddings and choices we do in designing hierarchies for those embeddings. So let me get into it here. And so this is going to be a little tiny bit more technical. So one thing you see is in machine learning systems that hierarchies are everywhere. So whether it's you can look at a lot of computer vision work or adopt hierarchies into their processes, where you see some work on actually building large language models where they take advantage of hierarchies, especially when you're using LLMs over chemical data. Same thing you can see in some of the usages of taxonomic data in natural language processing. So a lot of machine learning systems take advantage of hierarchies. Now, um, in this particular piece of work, we're going to look at using hierarchies within the context of hyperbolic embeddings, so geometry for hierarchies. This is used in a lot of computer vision applications. So we're not going to be in the Euclidean space, but in the hyperbolic space, and we're going to look at methods that take advantage of hyperbolic embeddings in order to do their processes. But that's not so important. It's important for the evaluation, but the key idea is that ML systems use hierarchies. Now, an interesting thing is the question is where do these hierarchies come from? Well, these hierarchies come from the folks on this call and in general larger, right? They come from knowledge graphs and ontologies, whether it be things like WordNet or schema.org or Wikidata. Essentially, people use off-the-shelf hierarchies. And so most of these machine learning methods, they kind of just assume the hierarchy is essentially given from on high, right? They just use it as is. But we all know that ontology engineers have control over the hierarchy, right? We actually choose what to do in when we build those hierarchies. We're encoding a lot of the knowledge we have about how to represent knowledge, and we have coming back to this word of the talk, taste, right? We think this hierarchy is better because it has a nicer representation of the things in the world. We think this hierarchy or this is better because it interlinks better. However it is, we're imposing our knowledge engineering view when we build these hierarchies or when we design the systems, right, that capture these hierarchies. So our whole take here is that in fact, we can change the hierarchies, which turns out nobody really thought about in the machine learning community, right? They just take it as is. So in a paper we published last year at ESWC, what we did was we said, well, could we look and see how we could modify the structure of an ontology, in particular the hierarchical structure, in order to improve the quality of hyperbolic embeddings, right? And you can, it turns out, and we came up with some restructuring recommendations. So if you have a given hierarchy, what can you do to make it embed better um, in a in hyperbolic geometry? So the recommendations were things like, you know, actually these methods, these hyperbolic embedding methods, they work well with hierarchies that are wide. It turns out that they don't really care about whether your uh, uh, hierarchy is balanced or not. You can have pretty big hierarchies. The embedding methods work well, right? And multiple inheritance seems to mess them up, right? So this was the kind of results from that paper. But now, so those are some recommendations. Now the interesting thing was, could we help knowledge engineers actually uh, use these recommendations, right? So these restructuring has better embeddings, but as a knowledge engineering, we have to do some more work, right? So can we help them? So the question was, how can we assist knowledge engineers in reorganizing hierarchical knowledge to improve these embeddings? And here we turn towards large language models, right? And so what we did was we're going to have uh, the hierarchy. We're going to put this hierarchy in a way that we can easily fit it to an LLM. And then we're going to prompt the LLM, and then we're going to do some validation afterwards. So what does that look like? So this is our prompt. And literally what we did was we took those recommendations that we wrote in the ESWC paper, we put it in our prompt. So design hierarchies for width. And we actually literally, I think, took exactly what we wrote in the ASWC paper and put it in the prompt, right? Um, and then, where is this? Why am I not seeing? Yeah, sorry. Um, as part of the prompt, we also want to do this post-prompt validation. So we wanted to ensure that the hierarchy that was produced by the system was different from the input hierarchy, right? So that there was some change. We wanted to make sure that the LLM didn't remove any of the leaf nodes, so it could adjust the hierarchy, but keeps all of the leaf nodes in the original ontology that was given. Uh, we didn't want any introduction of new nodes or edges, so to prevent hallucination. And we wanted the output format and the input format to be the same, right? So we had those checks as well, right, in our system. Now we experimented. So does this help? So if we have this assistance, does it actually help? So just to look at our experimental seven, we took 16 different hierarchies, different kinds, right? Ranging from pretty small to quite big, multiple domains. We did a couple different LLMs. We looked at state of the art in hyperbolic embeddings, and then we looked at two different quality metrics that are often used in hyperbolic embeddings to measure the quality of the embedding. So essentially, we're looking at this concept of distortion. Um, And essentially, what distortion looks at is, are the relative distances in your original hierarchy preserved in the actual space itself? And you look at the average case. So in average, what is the distortion and what is the worst case of the distortion? This DWC here. Okay, so this is the measure of our quality of distortion. All right. So we did these experiments. This is a big long table, right, of all of these different 16 different hierarchies, ranging from ImageNet hierarchies to the pizza ontology that we give everybody, right, when we teach them the semantic web, to hierarchies from visual genome, right? And what you see is, and these are the two different methods. And what you see is overall, you get an improvement, right? So over the quality of the embeddings, right? Let's look at this one example in a bit more detail. So this is the original hierarchy here, and this is the restructured hierarchy, right? So based on what we suggest, let me, um, so when we did what we show is that, the LLM guided restructuring reduced the number of modes, increased the depth, and also increased the branching factor. And that actually led to better quality in embeddings, right? So if you look at the D average, it improves, and the worst case, yeah, it improves as well for both of the different methods, right? So this is ChatGPT, and that's DeepSeek, right? And just to let you know, right, this is essentially the kind of higher quality embedding, and this is much faster to perform on these embedding quality. Um, the interesting question was, well, do the recommendations that we had, do they actually help, right? Or which of the recommendations that we had from this original paper, do they actually improve this performance, the embedding quality? And kind of the example is, where do these recommendations apply, right? For these different uh, ontologies, right? So what you see, or the way to say it is, this is the recommendation, this is the improvement, this is recommendation two, this is the score on that, and so on and so forth, right? And what the moral of the story, let's put, is all of the recommendations matter for improving the embedding distortion, right? Now, the interesting thing here is, again, this shows you that for these downstream tasks, our choices as knowledge engineers can have these kind of big impacts on what happens, right? And that's something to keep in mind, right? So, and we can also make different choices depending on what we're trying to do. Maybe we don't want to apply all of these recommendations because we have a different goal, right? We have a different knowledge representation that we're trying to achieve. Maybe actually adding that intermediate node is important for conveying the knowledge that we want. And so then there's this trade-off, right? And now we can have this LLM assistance that makes for those helps. Now, the interesting thing with LLMs is you can also have an explainable way. So this is an example is when we do this restructuring, the LLM can tell us why or the recommendation to do, and we can decide whether or not to do it, right? So we have this recommendation designed for width, not depth. Uh, your hierarchy has many deep, narrow chains. Uh, and it suggests flatten the deep chains where imminent nodes have a single child and no additional semantic weight, for example. Or go ahead and collapse these nodes, right? So it's telling you why it thinks it should do that to improve that performance, right? Um, uh, or we can have, for example, I'll do one more or explanation for you, right? Embedding performance is not simply by imbalance, and your hierarchy is naturally imbalances. So you don't actually have to do any. You can just retain the imbalance where it's semantically meaningful, where it's meaningful for the knowledge representation you're doing. So this sort of explanation of knowledge engineer can say, okay, here's some suggestions. What do you believe or what do you think is the best, and what are those trade-offs that you can make? All right. That was that example. Now I want to do one last example, and then we can have plenty of time for questions. And this is kind of very, very recent work. We haven't even published on it. This is the explanations. Um, uh, and this is about focusing and eliciting choice. Okay. Um, so this is work by Bradley Allen, also on our team. And this is very, very recent work. So this is called Ellenicus. I'm not, my Greek is not the greatest, so I hope I said that right. Um, and this is a protocol that Brad's built in Claude Code that essentially builds a Socratic, a dialogue with you as, let's call it a knowledge engineer or somebody who's acquiring knowledge. And what we're going to do is use GitHub issues as for better lack of a term, as the knowledge base. Okay. Um, so Claude is now going to become your intellectual sparring partner to produce knowledge. So it's going to track your commitments to particular facts and your denials. And what it's going to try to do is detects whether you're incoherent or whether you have coherence between what your commitments are to a particular piece of knowledge and whether you deny about the particular piece of knowledge. And it's going to challenge you, right? And it's going to, at the same time, maintain kind of a set of research questions that need to be answered in order to uh, acquire more knowledge in order to make a coherent knowledge base. And what it's trying to do is make sure that your choices, right, are always incoherent. And there's some deep kind of philosophical ideas underlying this idea, but I just want to show you an example more on the technical front of what you might do for ontology engineering or knowledge engineering. And so we're going to take one of my favorite ontologies, Provo, and we're going to talk about it. And this was when Brad did this, it was kind of very confronting to me as somebody who worked a long time on Provo. So this is going to track Provo dialectic states uh, in from the Provo ontology, from Prof. And we're going to have these commitments and we're going to have these denials. So let's look at this. You can actually go look at this repo on GitHub and have a look at all the commitments and denials. But let me show you an example. So the whole state is about 28 commitments and 16 denials. And so these are commitments. And see, this is just facts from the definition of prov, right? An entity is a class representing things with a fixed aspect. An activity is a class representing an activity or something that occurs over a period of time. There's this agent class. These are the three core types that are involved in prov. Agents and activities are not disjoint, and agents can also be agents and entities are not disjoint. So an agent can be an entity. Agents can also be activities. So these are some of the commitments about the prov ontology. So what is in the prov ontology? And now there's some of these deviles. So like Provo core defines domain-specific subtypes of entity, activity, and agent. So there are no agent domain-specific subtypes. These are not primitive classes in Provo, author or curator or publisher. It Provo it doesn't define workflow or process orchestration concepts, right? For example, provenance chains must terminate. It's not true in Prov. So these are our denials about what Prov is, right? So now a system will walk you through that when you're working with this on the command line. This is the result. These are all just stored in GitHub. And the system will challenge you, right? So here are some of the challenges that it produces about the coherence of Prov, right? It asks you like, what is the disjointness status of entity activity? So you said that they're not disjoint, and you also said these are not disjoint, but you have not stated whether entity and activity are disjoint, right? Are those completely separate, right? And where is this asymmetry? And what would be something example of both entity and activity? So is there coherence? This one particularly was challenging for me because in Prov, we had this notion of what's called a fixed aspect. And we said an entity is a things with fixed aspects that can be described. And there was, I remember a very long series of calls in the development of the standard about exactly this notion of fixed aspect. And it's asking, hey, well, what do you mean by a fixed aspect? Why do what is it fixed with respect to? Is it time or description? How does a fixed aspect relate to specialization? If some sort of aspect changed, does it become a different entity? So these are very good questions to ask about the coherency. So what we're doing in this tool is in some sense eliciting those choices, those design decisions, and trying to push towards being coherent in those choices when we do knowledge representation. All right. So this is kind of the kind of very state of what we're looking at. So can we make the taste that we have? Can we get that from us as humans? Can we use AI tools in order to do that? And I hope that what I've shown you is that with LLMs, with these AI tools, a lot more value comes from actually the decisions that we're eliciting from people and the taste that we inject, and that taste, how we design our knowledge graphs impacts things. So to wrap up, AI and LLMs have changed, I think, how we build knowledge graphs. Knowledge graphs have always encoded choice, right? This is not a new thing, but the value, I think, of KGs, especially in this era, come from the curation of these choices. And this impacts both knowledge graphs as information sources, and I think I showed you that in the longform.ai case, but also how those choices impact downstream chassis, how the choices we put in our hierarchies, in our graphs, and our knowledge graphs impact downstream tasks. I've shown you examples of some tooling, right, to help knowledge engineers make choices in different contexts. But this is just the start, right? So there's a lot more to do. Can we mine choices that already exist in knowledge graphs? So can we go out and look at Wikidata and see the choices that are underlying the schema there or in existing knowledge graphs? How can we best document these choices, right? Is it a set of GitHub issues, right, that I was just showing you, or some other way? Could we make it much easier for folks to explore the space of choice? With that, we have, I think, some time for questions. Really thanks for you coming, and thanks to the whole INDElab team for making this kind of work possible.